In this video, we're going to go through buffering capacity, and we're going to answer the question, how do the amounts and ratios of acid and base in a buffer affect its ability to resist changes in pH? So what is buffering capacity? Well, buffering capacity is how much acid or base a buffer can absorb without the pH changing by more than 1 unit. A stronger buffer has more ability to resist pH changes when acid or base is added. Remember, the whole purpose of the buffer is to resist change in pH. So the stronger the buffer, the more it's going to be able to resist those changes. Okay, so there are two ways to increase buffering capacity. Number one, higher concentrations of both the conjugate acid and base. In this scenario, the ratio is going to stay the same, so the pH is going to stay the same. We have more moles of either the acid or base available to neutralize the added acid or base. The other option is to use unequal amounts of the conjugate acid and base. If you have more of your conjugate base, it's going to be better at resisting acid when you add it. If you have more conjugate acid, it's going to be better at resisting base when we add it. So let's look at an example. It says you have 0.1 molar acetic acid and 0.1 molar sodium acetate. So this is that first scenario where we have an equal amount of acid and base. Calculate the pH before and after adding 0.05 molar NaOH. Okay, so let's begin by using our Henderson-Hasselbalch equation. Since this is a weak acid and its conjugate, we are going to use the Henderson-Hasselbalch equation. So to plug in, it's going to be pH equals pKa plus log of CH3 COO minus over our acid, which is HCH3 COO. Okay, we're going to need the pKa value for our acid here, which is 4.76. And we're going to plug in log, and we have 0.1 over 0.1. So we plug this into our calculator, and we get 4.76. Okay, so that would be before. Now let's do after we add our OH. So to do this, we're going to need a rice table. Let me shrink down and do this off to the side. All right. So we have HCH3 COO. Okay, so we had 0.1 molar of our acid and our conjugate. We're going to assume 1 liter here, so the moles of our OH are going to be equal to the molarity of our OH. We're assuming that we're not changing the volume here. So all of our base is going to get neutralized by the acid. So this is going to go down by 0.05. That's minus. And this is going to go down by 0.05. Okay, so then we plug in our values. Oops. So I forgot. Our conjugate's going to be going up because it's neutralizing with our acid. Okay. So now we're going to plug in our values. So now that we've solved our rice table, let's plug in what we have. So this time it's going to be pH is equal to pKa. So when we look that value up for our acid, it's 4.76 plus log our conjugate's value is 0.15, and our acid is 0.05. Okay, so when we solve, we get 5.24. Oops. All right. So initially, we had a pH of 4.76. When we added our NaOH, which is a strong base, that increased our pH by a little bit. Okay, so the buffer kind of did what it was designed to do. We had equal concentrations of our acid and our conjugate, and it was a relatively lower molarity because it was 0.1. All right, let's look at another scenario here. This time we have a higher molarity. So one of the two ways that we can increase buffering capacity is by increasing the concentrations. So we're doing just that. So we used 0.1 molar initially. Now we're going to try the same thing, but this time we're going to use a stronger concentration of our acid and our conjugate. Okay. So we want to know our pH before and after. So let's plug into the Henderson-Hasselbalch equation. This is a weak acid. So pKa is going to be the same. This is the same acid as before. So 4.76 plus log. It's 1 molar over 1 molar. So we're actually going to get the same value as we did before initially. 4.76. Okay. So now we're going to need to do a rice table. Our rice table is going to be slightly different this time because we have higher concentrations. So same species, but we just have higher concentrations this time. So it was HCH3COO, OH minus, and then CH3COO. Okay, so instead of 0.1, we now have 1 molar, and it's using the same concentration or the same number of moles of OH. So all of our OH is going to get neutralized by our acid. And then our conjugate will go up. So we'll have 0.95. This will be 0, and then 1.05. So now let's plug into our Henderson-Hasselbalch equation. So pH equals pKa. For this acid, it's 4.76 plus log. Okay, this time we have a different concentration. It's going to be 1.05 molar over 0.95 molar. Okay, so we plug this in. We get 4.80 as our pH this time. So if you recall from our first example, our pH changed from 4.76 to 5.24, and that was when we were using 0.1 molar of our acid and our conjugate. When we used stronger concentrations, when we used 1 molar instead, notice our pH went from 4.76 but only went up to 4.8, so a very small change. So what we can say here is higher concentration is better resistance. Okay, so that was the first way we can increase our buffer capacity. Okay, so the first way was to increase the concentration. Next, we're going to look at unequal amounts of our conjugate acid and base. Okay, so here we have 0.1 molar acetic acid and 1 molar sodium acetate. Okay, so here, let's find our initial pH, just like we did before. So pH equals pKa is going to be the same, 4.76. Okay, but it's not the same ratio. So we have 0.1 molar acetic acid and 1 molar sodium acetate. Okay, so plus log. This is going to be 1 molar over 0.1 molar. So here our initial pH is going to be 5.76, which makes sense because our base, our conjugate base, has a higher concentration. So of course, its concentration is going to be, or our pH is going to be higher, which means the concentration of our OH is going to be stronger in our solution. There's going to be more of it. Okay, so let's do our rice table. We're adding the same amount of NaOH as we have been. So let's make our rice table. Okay, so we had 0.1 molar acid. We were using the same amount of OH, and we had 1 molar of our conjugate. So our acid and our base that we're adding are going to neutralize. So this is going to go down to 0.05. This will be 0. This is going up by 0.05. So when we go to find our pH, let's see, our pH this time is going to be 1.05 over 0.05. So our pH here will be 6.08. Okay, so a slight increase in our pH. So we added a base, and we had a stronger concentration of our base. Let's do the same thing, but instead of adding a base, OH, we're going to add an acid this time. Okay, so instead of adding a strong acid, let's add a strong base, and let's see how it affects our solution. Okay, so it's going to be the same pH as before, 5.76. So we're pretending like we didn't add the NaOH here. So we're just going to go right to our rice table. Okay, plug in all of our initial concentrations. So we know our acid is 0.1, our conjugate is 1, and oh, wait a second, we're not adding NaOH this time. We're adding HCl. So HCl is going to give us H3O+. And we're using 0.05. Okay, this time our strong acid is going to neutralize with our conjugate. So I actually have this backwards, but you know what? This will work. I'm just going to leave it this way. I could have switched these around, but that's okay. All right, so our acid's going to go down. And our acid in our buffer is going to go up. So we are going to have 0.15. This will be 0, and then this will be 0.95. All right, let's plug this into our Henderson-Hasselbalch equation. 4.76 is the pKa for our acid. And let's see, conjugate over, so 0.95 over 0.15. Okay, so when I plug that in, I get a value of 5.56. Okay, so our original pH that we started with in our buffer was 5.76. When we used an acid, it only changed to 5.56. That's tiny. So we added HCl, which is an acid, and we had more base in our solution. So if we go back previously, when we added a base to the same buffer, it moved to 6.08. Okay, so let's look at the difference. So when we added a base, our pH was 5.76, and it went to 6.08. So, oops, let's take the absolute value of that because we don't want a negative number. So when I do that, I get 0.32. When I added an acid, it only changed by 0.2. So what I can say here is that if there's more base in our buffer, it's going to resist acids better, and vice versa would also be true. So we wrote this down earlier. If you have more conjugate base, it's going to be better at resisting acid when it's added. And then if you have more acid, it's going to be better at resisting added bases. And that's buffering capacity.